So now we're going to look at how to calculate the equivalent resistance and then the current through and voltage drop and power dissipated by each resistor in a relatively simple parallel type hybrid circuit. In other words, the simplest type of hybrid circuit in which you're dealing with basically parallel elements as the main theme of the circuit. And here's what we mean by that. If you look at the battery and you follow the current coming out of the battery, the current comes out of the battery, goes clockwise like this, it meets this junction. It now has a choice. It can either go through the 15 ohm resistor or it can go through these two resistors up here. So it's an either or type of thing. So the main theme for this circuit is that it's going to be a parallel type of hybrid. So we write down our givens, and then we realize again that the 15 ohm resistor is in parallel with this stuff up here. In fact, that's the name that we're going to give it. So in order to be able to calculate the equivalent resistance of the circuit, we need to use the parallel formula, but we also need to know the equivalent resistance of this stuff up here. In fact, if you're looking at that directly, you can probably already just see that that's going to be 40 ohms. So we calculate the equivalent resistance of stuff, and you get 40 ohms. And now we're going to plug that into that formula that we just had on the previous slide, that 1 over the equivalent resistance of the whole circuit, since it's basically a parallel type of circuit, is equal to 1 over resistance 3, which was our 15 ohm resistor, plus 1 over the resistance of stuff, which turned out to be 40 ohms. Well, we find a common denominator here. We'd love to use 60 ohms here, but unfortunately 40 does not go into 60 evenly. So the next step up is going to be 120 ohms. So 120 turns out to be our common denominator here. So in order to get 120 out of 15, well, you need to multiply top and bottom by 8. In order to get 120 out of 40, you need to multiply top and bottom by 3. And then when you add that together, you get 11 over 120 ohms is 1 over the equivalent resistance. So the equivalent resistance turns out to be 120 ohms over 11, or 10.909090909, or about 10.9 ohms. Now, you might be wondering, what if I don't get the least common denominator? Can't I just multiply the 15 and the 40 together to get 600 and do 40 over 600 ohms plus 15 over 600 ohms? Why, yes, you can. And if you do that, you'll end up getting 55 over 600 ohms, which reduces to 11 over 120 ohms. So if you do come up with the least common denominator, there's a good chance that your answer is actually going to be in reduced form. Not that it really matters, because you're about to shove it into a calculator anyway to get 10.9 ohms, but just mentioning that. So we found the equivalent resistance of our circuit. So next, it's usually good practice to find the current coming out of the battery. So we're going to do that here. It turns out it's 2.52 amps. Turns out we didn't need that, but because we don't have anything that's directly in series with the battery, but it's good practice anyway. So in case you had any doubts, you could multiply the 2.52 amps by the equivalent resistance of the whole circuit, or at least of this whole thing right here, stuff in parallel with 15, and you'll end up getting 27.5 volts, but you already knew that. Anyway, next, it's good to note that, well, you have stuff in parallel with the 15 ohm resistor. Well, if the current comes out of the battery and it decides to travel through the 15 ohm resistor, it's going to undergo one drop all at once and go down to 0, which means the voltage drop through the 15 ohm resistor must have been 27.5 volts. So we know that immediately. Now, we also notice that stuff is in parallel with the 15 ohm resistor, which means that the total voltage drop through stuff is 27.5 volts, and again the total voltage drop through the 15 ohm resistor is also 27.5 volts. So Doing this, we can figure out the current that's going through stuff. We could also figure out the current that's going through the 15 ohm resistor. But by figuring out the current that's going through stuff using Ohm's law, V equals IR, so I equals V over R, so the current going through stuff is the total voltage drop across stuff, which is 27.5 volts. So like if you put the positive terminal of your voltmeter right here to the left of the 30 ohm resistor and the negative terminal to the right of the 10 ohm resistor, you would get a voltage drop of 27.5 volts. Well, divide that by the equivalent resistance of stuff. That'll give you the current running through stuff. Well, that's the current through the 30 ohm resistor and the current through the 10 ohm resistor, because again, whatever current goes through the 30 ohm resistor has to also survive to get to the 10 ohm resistor. So those currents are the same. So 0.69 amps is going through each of those resistors. And that's also just the current that's going through this branch that we're calling stuff. Now, the current going through the 15 ohm resistor is found the same way. We know we have a 27.5 volt voltage drop across this one arm, and there's only one resistor in that arm, so 27.5 volts divided by 15 ohms, that gives you 1.83 amps. Now notice that if you were to add together the current going through the 15 ohm arm and the stuff arm, you would get 2.52 amps, which was exactly the same as the total current coming out of the battery. In other words, the current came out of the battery is 2.52 amps. It split up. 0.69 amps of it ended up going up this way. The other 1.3 amps, or sorry, the 1.83 amps ended up going through the 15 ohm resistor. So now that we know, well, we already know the voltage drop across the 15 ohm resistor. That's what allowed us to figure this out. Now that we know the current going through stuff, we can find the individual voltage drops across these resistors that are a part of stuff. So you might be thinking, well, didn't we already calculate that, 27.5 volts? No, we calculated the total voltage drop across stuff, the total drop in height in this waterfall. But there's one drop here across the 30 ohm resistor. There's another drop here across the 10 ohm resistor. So it's like a one waterfall, the river levels out, and then there's another waterfall. So that's what we do next. We calculate the voltage drops across each of those two resistors, which I must mention had better add to 27.5 volts. Well, we'll make sure that they do. Well, sure enough, V equals IR. So the 30 ohm resistor was the one that we called resistor 1. The 10 ohm resistor was what we called resistor 2. So V1 equals I1R1. Well, the current is the same in each of these because they're in series. And when you multiply those together, you get 20.6 volts across the 30 ohm resistor and a voltage drop of 6.9 volts across the 10 ohm resistor. And notice, not surprisingly, these add to 27.5 volts. In other words, the total voltage drop is the same whether the water decided to go through this branch of the river and drop twice in little baby successions along the cliff, or whether it went into this branch of the river which just dropped from the top of the cliff to the bottom of the cliff in one fell swoop. You get the same voltage drop. So now we calculate the powers. We can do that. PIV, that's easy to do because we've already figured out each of the individual currents and each of the individual voltage drops, so we calculate those through. Notice that we had the same current in resistor 1 and resistor 2, the 30 ohm and the 10 ohm, but we have a different current in resistor 3, the 15 ohm, and different voltage drops through all three resistors in this case. So again, if you really wanted to know the total power consumption for this circuit, that would end up being just the sum of each of these individual power consumptions. So adding together P1 and P2 gives 18.93. Adding that to 50.4 watts ends up giving 69.33 watts of power is what's being consumed by the whole circuit. So the rate at which energy is being consumed out of this battery, because remember, a watt is a joule per second. So that's how you figure out the equivalent resistance for a parallel type hybrid circuit and the current and voltage drop through each individual resistor, as well as the power dissipated by each of the individual resistors. So I hope these videos were helpful, and thank you for watching.